All right, so let's continue our discussion related to biasing of BJT amplifiers. And we've been looking at these two different ways of biasing. One is what we call as the fixed resistor bias, and the other one is the voltage divider bias. And the voltage divider bias here is well known that this particular circuit here makes the biasing insensitive to the beta of the transistor. We know that the beta of bipolar transistor can vary a lot, and we want biasing to be stable. And this particular circuit, the voltage divider bias, allows us to make the biasing in the sense that the collector, DC collector current and collector emitter voltage, if the circuit is designed properly, becomes insensitive to changes in beta here. But we had also, what we were discussing was that whenever you get something, you also lose something. There are always trade-offs in design. And in that context, in an earlier lecture, we had seen that yes, we are able to get beta insensitivity through this circuit number 2, voltage divider bias. But there are several things that we lose in the process. One of them is that the circuit is more sensitive to variations in the resistance itself. Right? So besides the beta of the transistor, the resistors also have tolerances, and they also vary. And they will also cause the bias current and the voltages to vary also. And it's in our interest to keep the bias point stable. So this is also important here. But the circuit number 2, the voltage divider bias, makes the bias point more sensitive to variations in resistance as compared to the fixed resistor bias. And that is because in the fixed resistor bias, the collector current is determined by only one single resistor, which is RB. And so variations in only one resistor affect the collector current. While in the second circuit, the collector current is determined by R1 and R2 and RE. There are 3 resistors. So variations in all 3 resistors contribute to changes in collector current. And that makes the circuit more sensitive to the tolerances in the resistors. Similarly, circuit number 2 is more sensitive to variations in base emitter voltage. We had seen that the base emitter voltage changes with temperature, and circuits are expected to work over a large temperature range, let's say from 0 to 70 degrees. And in circuit number 1, in this case, what we get is the collector current is VCC minus VBE by RB times beta here, right? And so VBE, if we look at VBE, it subtracts from the full collector voltage here, VCC, right? And so any change in VBE has less effect on the collector current. While in circuit number 2, we know that IC is VCC R2 by R1 plus R2 minus VBE divided by RB by beta plus RE here. So now the impact of VBE is much larger because this voltage here that you see here is much smaller here. And any change in VBE will then cause a more change in collector current. So the circuit number 2, the voltage divider bias, is also more sensitive to variations in base emitter voltage and more sensitive to variations in R. So this is the point that we are trying to emphasize, that when you solve a particular problem, you end up creating other problems because there are trade-offs. You end up making things worse. So in continuation with that particular thought process, in fact, the voltage divider bias, one of the key trade-offs in voltage divider bias, or the key loss in voltage divider bias, is that when you implement this particular biasing scheme, you end up losing gain, and you end up losing swing also. So besides the other points, more sensitivity to resistors, more sensitivity to base emitter voltage, you end up with these problems also. So in order to explore that and in order to illustrate that, what we need to do is carry out the biasing design for these two different approaches. So we are comparing our fixed resistor bias, this one here, versus the voltage divider bias here. So the design of these two circuits needs to be carried out properly, otherwise the comparison may not be fair. So what we are going to do is we have fixed the supply voltage to 9 volt here. In both cases, both circuits are driven by the same supply voltage, because we are going to compare the gain and the swing, for example. These two quantities we want to compare. So in order to compare it in a fair manner, so both of them are being driven by the same supply voltage 9 volts, let's say. Later on we'll change the voltage also, but we'll keep the voltage same between the two circuits. And then we'll design it for a fixed value of ICQ, for a given value of ICQ. So ICQ is going to be the same in both cases. Okay, beta is same in both the cases, right? Beta is also same in both the cases here. And after that, what we are going to do is, so once you design ICQ, we'll consider that the voltage that is available divides equally between VCE here and the drop here. So when we have 9 volts, we'll divide 9 volts equally between the collector emitter voltage and the resistor RC. So this is something similar to what you would have seen as biasing in the middle of the load line, right? So that particular approach. So we have 9 volts, so VC equal to 4.5, and the drop across the collector resistance ICRC is 4.5 also. So the design of the first circuit is straightforward, given a particular value of ICQ. If we are given ICQ and we are given VCC here, and base emitter voltage we'll assume to be equal to 0.7, and then from there, and beta is given to us, so then the RB is straightforward determined. And RB is determined here, and VCQ we are going to set in the middle, so VCQ is 4.5, so then RC is also determined, right? So the design of this is fairly straightforward, the fixed resistor bias here. The design of the voltage divider bias is more complicated, right? And so here, for example, let's look at a systematic way of determining R1, R2, RE, and RC here, right? So design of bias circuit. So let's look at that bias circuit here, right? So let's look at that. So one of the first choices that one has to make is, note that the sensitivity of ICQ depends on RB, it depends on how much RE versus RB by beta here. We'll ignore the beta plus 1 factor here. So RE plus beta here. The larger you make RE compared to beta here. So let's make this factor XB here. So the higher the factor XB is, the more insensitive the circuit becomes to changes in beta here, right? So that's one of the choices here. For example, if I make XB equal to 10, you will have a certain sensitivity of circuit to beta here. If you make the sensitivity XB equal to 100, the circuit will become even more insensitive. So depending on how much insensitivity you want, you choose a value of XB here, right? So XB is chosen according to that. So that's the first choice that you have to make. The other one is, note that input resistance is also an important parameter. So input resistance is R pi parallel RB, right? And R pi is VT by ICQ times beta here, right? So note that ICQ is given to us. We are designing the circuit for a particular value of ICQ, and VT, beta, everything is known, so R pi is fixed here. So if you want to get a large value of Rn, the highest value of Rn that you will get is equal to R pi. But that will occur if you make RB much, much larger than R pi. So the other choice that is there before us is, how large do you want to make, let's say Xn times R pi. How large a value of RB do you want to choose compared to R pi that is given here? Okay, so that's the other choice that we have to make. Well, if you choose Xn equal to 1, then the input resistance will be reduced to R pi by 2. If you made Xn equal to 10, then the input resistance would be maybe some 0.9 times R pi. And beyond a certain value of Xn, it doesn't really have any impact because R pi isn't parallel with that particular resistor. So that's the other choice that you have to make. How large an RB do you want to make compared to R pi? Now these two choices, you will see, determine the value of the emitter resistance and the value of RB also. So what we can do is as follows. So RB is Xn R pi, right? So we can write RB is Xn Vt by ICQ beta here, right? We can write it this. And this one we can write as Rb by beta equal to Xn Vt by ICQ. Now Rb by beta, we can take it from here. Rb by beta is Re by Xv. So we can get here Re by X equal to Xn Vt by ICQ. Right, and therefore we can get Re equal to Xb Xn Vt by ICQ. So that's the point that we are trying to make here, that the moment you make these choices, how much beta insensitivity do you want, and how large an Rb do you want to make compared to R pi here, you will get the value of Re. And once you get the value of Re, note that you will get the value of Rb, because Re and Rb are related together here, right? So the moment you get Re, you get Rb here, right? So that allows us to complete the design here. So this is what we are saying, that you have to make the choice of Xb and Xn. And once you make that particular choice, you will get the value of Re and you will get the value of Rb. And the moment you do that, if you go back to this equation number 1, let's say, this particular equation, so we can take that particular equation and we can write this as ICQ Rb by beta. So Rb by beta here, ICQ times Rb by beta plus 1 plus Re equal to VCC R2 by R1 plus R2 minus VB, so let's take it 0.7. So note that we know ICQ, we know Rb, we know Re, we know 0.7. So you end up getting this ratio, and we know, so you'll end up getting R2 by R1 plus R2. You'll get this value. And we already have determined Rb. Rb is R1, R2, R1 plus R2, right? So from these two equations, we'll get the value of R1 and you'll get the value of R2, right? So that's how we are able to determine these resistors here, R1, R2, and Re here. And everything depends on this particular choice here, Xb and Xn. How large you want to make Re, how large an Re you want to get compared to the Rb by beta here, and how large an Rb you want to make compared to R pi here. So these choices, they decide the value of Re, and then all the other parameters that are there here, Re and then R1 and then R2. And note that once you do that, once you make these choices, ICQ Re according to this equation is Xn Xb times Vt, right? So in our design, what we will do is we will take the value of Xb to be 10 and Xn to be 10 here. So we'll make Re 10 times Rb by beta, and we'll make Rb also 10 times the value of R pi here. And so we will get V equal to 2.6 here. So that's a reasonable design, because the circuit is reasonably insensitive to beta, and Rb also then doesn't have much impact on the input resistance because we've taken it 10 times. So that makes VE equal to 2.6 volt here. So that gets fixed here, right? So this voltage here becomes fixed at 2.6 volt here. And the remaining voltage that I have, so the remaining voltage is here and here. So we have 9 minus 2.6. So that remaining voltage we divide equally between the collector emitter voltage and the drop here, right? So 9 minus 2.6 we will get as, so 9 minus 2.6 will give us 6.4. So half of it. So we'll put 3.2 here and we'll put 3.2 here, right? And so that completes the design. So 3.2 is VCEQ and 3.2 is the drop here across the resistor RC here. We already know ICQ RC is 3.2, so we will determine the value of RC here. Okay, so that's how we end up creating a design for the voltage divider bias here. So let's show you an example. So we have done a design for ICQ equal to 1.76 milliamperes here. And the same design we are doing in voltage divider bias also at 1.76 milliamperes here. And as we said, 4.5, half the voltage 4.5 is dropped here, the other 4.5, we divide it equally, so VCEQ is 4.5. And then we can get the, from once we do the design, we can get the value of the magnitude of the voltage gain is GMRC. GMRC, so we get 173. And input resistance is RB parallel R pi, so we get 1.47 kilo ohm. And power dissipation also we are calculating 16 milliwatts, so it's basically equal to the VCC 9 volt multiplied by the total current drawn from the supply here. So that gives us 16 milliwatts here. All right, let's look at the second design here. In the second design, using the approach that we talked about, we had set this value equal to 2.6 volt. And we obtained the value of R1 and R2 and RE, all on the basis of ICQ equal to 1.76 volt and V equal to 2.6 here. The remaining voltage between here and here we just said is equal to 6.4 volt, and the 6.4 volt we divide equally. VC equal to 3.2 and ICQ RC is also 3.2. So it's like biasing in the middle here. So with that design, we get all the values of R1, R2, RC and RE. So we get gain of 123 here. Note that there is a 29% loss in the gain here. We get a gain of 173, we gain a gain of 123 here. So that's the point that we were trying to say, is that when we try to design for beta insensitivity, the voltage divider bias, we end up with several losses. Some of the losses we had seen earlier, but in this particular lecture we are seeing that we get a loss in the gain. And the result for the loss in the gain is that because we have put a resistor RE here, so there's a drop here, 2.6 volt, which means that there is less voltage now across RC. And less voltage across RC, note that the gain GMRC, if we write, is nothing but equal to ICQ RC by VT. So it depends on the drop here, ICQ RC. So when we have an emitter resistance, we get a drop here, so we get less voltage across RC, and that translates into less gain here. We get a input resistance of 1.34 kilo ohm, and as compared to 1.47, this is about 9% lower. And power dissipation is a little bit higher, 17.2, so 7% higher here. So what we are seeing is that we get a loss in significant loss in gain, and some loss in input resistance, and some increase in the power dissipation. And the other thing is that we get a lower voltage swing. Now voltage swing is more complicated. We have a separate lecture which discusses that. But the upper limit on voltage swing is the collector emitter voltage. And the collector emitter voltage is, swing cannot exceed the collector emitter voltage. So it is 3.2 here, it is 4.5 here. So we get a loss in voltage swing. We get lower voltage swing also. So the voltage divider bias, and these problems become worse when you go to lower supply voltage. Here we have taken 9 volt. Now if we use a similar approach and design it for 5 volt here, right? So we have done the design for 5 volt here. And we have done the design for current equal to close to a 1 milliampere here. VC equal to 2.5, 2.5 here and 2.5 here, right? And the gain here is 96.1. Input resistance is 2.8 K. Same approach we had used here. Same current. ICQ is in the voltage divided by 0.91 milliampere. Same approach. We set the emitter voltage as 2.6 volt here to get beta insensitivity and also to make the RB 10 times higher than R pi. And so what we get is, note that we get a gain of 46.1 here compared to 96.1. The gain is almost half of that of fixed resistor bias. The input resistance, there's a loss about 8.5%, power dissipation is 2.9% here. So there's a very, very large loss in the gain because we have gone to lower supply voltage here. And there is a large loss in voltage swing. Note that the VCE is here 2.5 volt while the VC is 1.2 volt here. So there's a large loss in the swing also. So that's the point that we are trying to make, is that when you try to, when you use a voltage divider bias and you implement a negative feedback and you get beta insensitivity, you end up losing other things in the circuit here. And it's important as a designer that one is aware of the trade-offs, the price that one is paying for getting something which is positive here. And so in summary, and that brings us to also this particular circuit. Some of you would have seen a circuit like this here. This circuit is simpler than voltage divider bias. In the voltage divider bias, there is an additional resistor here, right? There's an additional resistor here connected, that is there here. And one may wonder why, for example, this particular circuit is not used. It's simpler than the other one. And if we were to analyze this particular circuit, we get ICQ equal to VCC minus VB RB by beta plus RE. So if you look at the denominator, it's very similar to the voltage divider bias. And all we need to do is make RE, just like in the voltage divider bias, RB by beta. And we get a circuit which is beta insensitive, right? Just like the voltage divider bias. So why do we not use this particular circuit? And the reason for this is clear, because what happens is you should not just look at the beta insensitivity. As we are saying, there are many other factors that are there, right? We looked at voltage gain, input resistance, swing, and all of those things that are there here. So very quick analysis will tell you that if you look at this particular equation here, right? So if you try to make RE much larger than RB by beta here, suppose we do that, then ICQ will primarily become VCC minus VBE by RE, right? We made the circuit beta insensitive, which means that ICQ RE equal to VCC minus VBE. Now this ICQ RE is nothing but the emitter voltage here, VE, right? This is the voltage here, VE here. So this is equal to VCC minus VBE. And if we look at here, we know that VCC equal to ICQ RC plus VCEQ plus VE here, right? If we substitute this value of VE, then what we get is ICQ RC plus VCEQ equal to VBE equal to 0.7, right? So the drop from here to here is about 0.7 here. And again, if we do a biasing in the middle, then it would mean ICQRC is 0.7 by 2 equal to 0.35, and VCEQ equal to 0.35, right? So what you see here is that VCEQ becomes very small, 0.35. So you hardly get any swing. VCQ is very close to VCE sat, and you get very little swing here. So that's the first problem. The other thing is ICQRC is 0.35, and the gain, the magnitude of the gain is ICQRC by VT. And so this you will find is only maybe 13 or so. So you get very low gain here, right? So you get very low gain and you get very low swing here. So that's the price that you end up paying. If you look at this particular circuit, if you try to get beta insensitivity and you make RE much larger than RB beta, you hardly get any gain, you get very low gain, and you hardly get any swing here. And that's the reason why we don't use this particular circuit here. This circuit is not very useful. And to solve that particular problem, we add this particular resistor here. We add a resistor R2 here to solve some of these problems here. All right, so as a summary, this circuit, this very popular circuit voltage divider bias, it gives us beta insensitivity, right? Beta insensitivity. But we should also see that it has some disadvantages. So what are the disadvantages? There's loss in gain, loss in voltage gain. And this loss is especially very large once the VCC, especially for smaller VCC, smaller supply voltage. So that's the first loss that we get, a loss in VCEQ, and therefore we get a loss in swing. That also becomes very prominent when we go to lower VCC. And of course, we get some loss in Rn input resistance and increase in power dissipation, P dissipation. These are also there. But we have properly designed this particular bias circuit. So this is not so, these are not so, significant. But this is very significant here. Loss in voltage gain and loss in VCQ. And we had seen earlier that the circuit is more sensitive to R1, R2, Re, the resistances that are there. Circuit is more sensitive to variations in VBE here. Right, so it's important to note this trade-off that is there here, that one is able to get something, but there is a price that has to be paid for that positive feature of beta insensitivity. All right, so let's stop here.